physics people, welcome back. This is projectile motion. This is our two-dimensional kinematics. We'll start with projectile motion, and then our next PowerPoint will be centripetal acceleration. So as you can see in the thing here, something is shot horizontally. If you're watching the numbers there, as the time increases, the velocity in the y direction increases, but the velocity in the x direction stays the same. And we'll talk about why that is as we move on through the PowerPoint. A projectile is any object which projected by some means and continues to move due to its own mass or inertia. So any object that's projected by some means, a tennis ball being thrown, a catapult throwing a rock, something like that, a projectile, an arrow, things like that. So projectiles move in two dimensions. As I said before, this is two-dimensional kinematics. Therefore, it has two components, a horizontal and vertical. If you notice, you look at the red arrow as the vertical. As it goes up, that red arrow gets shorter till it reaches the top, and then as it goes down, it gets bigger again. And if you notice that the horizontal component never changes, it stays the same throughout, and we'll talk about that. Horizontal velocity component, it never changes. It covers equal displacements in equal time periods. So that means the initial horizontal velocity equals the final horizontal velocity. It does not change for a projectile. So if it moves 1 meter in 1 second, it's going to continue to move 1 meter in 1 second till it hits the ground. So the horizontal velocity is constant. And that's because gravity does not work horizontally, it only works vertically. So it does not decrease the velocity in the x direction. And there's no friction in the air, or it's negligent to speak of, so our horizontal velocity stays the same throughout the projectile's travel. The vertical velocity, on the other hand, does change, and that's because of gravity. So if you look at the thing here, it says it does not cover equal displacements in equal time periods. If you look, after 1 second, it covered 5 meters. After 2 seconds, it covered 20 meters. 3 seconds, 45 meters. And you say, well, why is that? And that's because both the magnitude and direction change. So as the projectile moves upward, the magnitude decreases and its direction is upward. But as it moves down, the magnitude increases again and the direction is downward. So the acceleration you can think of is always due to gravity, and so that's why it moves different intervals over different time, or different distances or displacements over the same time interval. So combining these components together, the components produce what is called trajectory, or its travel or path, and the path is always parabolic in nature. So as you can see in the little chart in the bottom, the horizontal component, the magnitude, is always constant and the direction is constant. And for the vertical, both change. So the magnitude of the acceleration changes and velocity changes and the direction changes. So it's always changing, as you can see by the arrow getting shorter, that the direction is not, and then it falls. So the magnitude is getting, the arrow getting shorter means the magnitude is decreasing till it gets to the top where it's 0, and then as it falls down it starts to increase again, and the direction changes once it reaches its peak. It goes from going upward to going downward. So horizontally launched projectiles, they're the easiest to do, and we'll talk about why when we get to the equations. So projectiles which have no upward trajectory and no initial vertical velocity. So that's like taking a tennis ball and throwing it straight off the top of a building straight outward. There's no vertical velocity in the upward direction. So that's a horizontally launched projectile. So the initial velocity in the y direction will always be 0. So you can see initial velocity in the y direction, 0 meters per second. So the velocity in the x direction is equal to the initial velocity in the x direction, and it's constant. So let's say I threw this tennis ball at 25 meters per second at the top arrow there. If you go all the way down to where that bottom arrow is pointing horizontally, it is still 25 meters per second in the horizontal direction. So it never changes. So to figure out how to find horizontally launched projectiles, we have to know some equations. We already know them. We're just going to put a few different variables in there to annotate that these are projectiles. We need two equations, one for the x direction and one for the y direction. And so we already talked about these. So x is equal to the initial velocity in the x direction times time. So since the horizontal velocity is constant, has no acceleration, the second half of that equation does not apply. The 1/2 acceleration times time squared, I have 0 acceleration, so it eliminates that. But by the same token, the velocity in the y direction, initial velocity in the y direction is 0, so that first part, the initial velocity times time is 0, so I end up with y is equal to 1/2 times gravity times time squared. X tells me how far it goes in the x direction, or its range, and y is going to give me the height of, say, a cliff or something, or a building that this projectile was launched off of. So we can use those equations to find that. So no vertical velocity, it's equal to 0, so we end up with 1/2 gravity times time squared. So this is just our displacement equation, just kind of rearranged to fit what we need here by knowing that the initial velocity in the x direction is constant and it has no acceleration, and knowing that the initial velocity in the y direction is 0, but I always have acceleration due to gravity. Alright, so we got an example problem here. A plane traveling with a horizontal velocity of 100 meters per second is 500 meters above the ground. At some point, the pilot decides to drop some supplies to a designated target below. How long is the drop in the air, and B, how far away from the point where it was launched will it land? So we can solve for both of these. So I want to know the time. What I do know, initial velocity in the x direction, 100 meters per second. My height, or my y, is 500 meters. Initial velocity in the y direction is 0, and gravity is still 9.8 meters per second squared. So I want to know the time, and I want to know x, which is called range. So I have to plug in a few things. So I take my equation, y is equal to 1/2 gravity times time squared. I plug in my numbers, negative 500 because it's falling to the ground, is equal to 1/2 times gravity, which is negative 9.8 times time squared. And I end up with, when I do the math, what I'm going to do is I'm going to multiply 1/2 times negative 9.8 gives me negative 4.9, and I'm going to divide negative 500 by negative 4.9. And that gives me 102.04 equals time squared, but I want to know time, so I'll take the square root of it, and that gives me 10.1 seconds. To find the range, my initial velocity in the x direction is 100 meters per second, and I know my time now, 10.1 seconds, so I'm going to plug that in, and it's going to give me 1,010 meters is how far from where it was dropped. So these equations are just our kinematics equations we already know. We just have to plug in the numbers and use the appropriate equation. Continuing, now we got to deal with vertically launched projectiles. So in this case, our horizontal magnitude of velocity is still constant, and our direction is still constant. It's still horizontal. Our vertical, the magnitude decreases, and it's 0 at the top, and then increases on the way down. And the direction changes, as you can see by the arrows. On the way up, they were pointing upwards, and on the way down, they're pointing down. Still the same thing we talked about earlier. So horizontal velocity is constant, vertical velocity decreases on the upward, and increases on the way down. So there is no vertical velocity at the top of the trajectory. I kind of talked about this before when I threw the tennis ball up. At the very top, it stops, and then it falls back down. So we have vertically launched projectiles, or launched at angles, and they have components. So now, to find the initial velocity in the x and y direction, we have to use the sine and cosine to find those. So the initial velocity in the x direction is equal to the initial velocity, whatever number they give us, times the cosine of whatever angle they give us. And the same for the y direction. The initial velocity in the y direction is whatever initial velocity they give us times the sine of that angle. And then we can solve for those and then plug them back into those same equations we already learned to find the range and those things like that, and the maximum height, and we'll talk about that. So there are several things you must consider when doing these types of projectiles besides using components. If it begins and ends at ground level, the displacement in the y direction is 0, and that's what we'll mostly deal with, where they launch from some angle and they land some distance away. So our displacement in the y direction, our max, that's okay. The y displacement is 0. We'll just stick with that for right now. Alright, because it went up and it came back down, and it's back at the same place it started. Alright, so still use those same kinematics equations, but now we use, instead of just saying initial velocity is what we were given, we find it using those two equations. Same for the y component, but now instead of it being y is equal to 1/2 times gravity times time squared, we have to plug in that initial velocity of y times time because it matters. In the range equation, our acceleration in the x direction is still 0, even though it's vertically launched. We have no acceleration due to gravity affecting it. So same equation, just a different way to find the initial velocity. Alright, so here's our example. A place kicker kicks a football with a velocity of 20 meters per second at an angle of 53 degrees. How long is the ball in the air is the first question we want to answer. How far away does it land? That's its range. And how high does it travel? That's also called maximum height, and we'll talk about it. So our diagram shows where it was kicked. So we need to first thing we need to do when we get a problem like this is find our initial velocities. So we plug in our information. Initial velocity in the x direction is equal to initial velocity cosine of theta. So we put equals 20 meters per second. That was our initial velocity times the cosine of 53 degrees, which is our angle. And that, if you work that out, it gives us 12.04 meters per second. And for the y direction, the same thing, but now we use a sine of theta, and we end up with 15.97 meters per second. So that gives us our initial velocities. Now we can go back and plug those into our equations to help solve for it. So the first thing we want to know is how long is the ball in the air. We want to know time. So we take our equation, y is equal to the initial velocity in the y direction times time plus 1/2 gravity times time squared. We know our displacement in the y direction, since it hits the ground, is 0. So that y is just like displacement. So we put a 0 in for that, equals 15.97, our calculated initial velocity times time, minus 4.9 times time squared. Now we have to solve, so we're going to move the one of these to the other side of the equation. This example, they moved the 15.9 and made it negative 15.9 t by subtracting it from both sides, equals negative 4.9 times time squared. You also could have simply added 4.9 to both sides and ended up with 4.9 times time squared equals 15.97 times time. Then we're going to divide both sides by 4.9 t. So that eliminates our time squared, and then our answer works out to be 3.26 seconds. So you could have simply divided by t the first time to eliminate the t squared, but I just like to do it all at once, and I would have divided both sides by negative 4.9 t, or 4.9 t if you did it the other way. And so now we know our time. The second question we want to know is how far away it lands, and that's called range. The range equation is displacement, or x, is equal to initial velocity in the x times time. So we plug in our numbers. We figured out our initial velocity in the x direction was 12.04 meters per second. We multiply it by time, which is 3.26 seconds, and that works out to be 39.24 meters. So now we figured out two things. We figured out our time, and we figured out our displacement, or our range. Now, our range, or our displacement in the x direction, I should say. Displacement in the y direction is 0. Now we want to know how high it's traveled, and that is called max height. The trick to max height is, when does the football reach its maximum height? And that is halfway through the time interval, because the 3.26 seconds is how long it took for it to be kicked until it hit the ground again. So when we do this, we have to make sure that we cut our time component in half. So we still use the same equation. Our displacement in the y direction is equal to initial velocity times time plus 1/2 gravity times time squared. In this case, our displacement in the y direction is not 0, because we want to know the maximum height. So we plug in our information. Our initial velocity in the y direction is 15.97 times 1.63 minus 4.9 times 1.63 squared. And if you do all the math on that and work it out, you should have gotten your maximum height was 13.01 meters. Now this is all we're going to learn for right now on projectiles. We'll talk about a few other things in class. So I suspect you'll have these notes, and we'll see you next time, and have a great evening.